So far we talk about real valued function. How about vector valued function? We consider vector valued function. F is a map from a neighborhood of A to another Euclidean space Rm. So this is a an independent variable and dependent variables function. Okay, so such a function can be determined by its components. As this vector valued function equivalent to m real valued function. Here all the fi are real valued. Okay, so if for every I every j if for j equal to 1 m, the ith partial derivative of fj with respect to xi at this point A exists. I is fixed. I is fixed. Remember, I is fixed. Fixing this I, we consider j equal to 1, 2, until m. If all these partial derivatives exist, we can have a vector. Okay, we get a vector denoted by dif a just like our previous notation. But remember, in our previous discussion, f is a real valued function. But now our f is a vector valued function. So what's this? This is the vector whose component or coordinate is the partial derivative of the components of f at this point A. Okay? So the meaning of all these are known to us. We have just discussed this because f1, f2, fm are real valued function. We know what is partial derivative at this point A means. Okay. Now, if all these exist, we fit them together to get a vector denoted by this using the same notation. So this vector also called partial derivative of the vector valued function f at the point A with respect to, of course, xi. Okay, the same as the real value case. But now what we consider is a vector value case. So if for in this discussion I is fixed, if this is also true for every I, so next, if the partial derivative exists for every I, of course I is 1 until n. Okay, then we have n vector. We have n partial derivative vector for this vector valued function. They are d1f a until dnf a, right? We have this n partial derivative, all of these are vectors. Okay, so we use this vector as a column to construct a matrix. The m, this matrix is m by a matrix. What's this? Okay, and maybe I change. The color is not good. I will erase this. Okay. This matrix we denoted by f prime a. We use this notation. This notation is the same as our notation for derivative in our study of single variable functions. We will explain this later, but we just use this notation here. Okay. So this matrix is called the Jacobian matrix of f at a. Of our vector valued function at the point a. Okay. The Jacobi matrix. So for the Jacobi matrix, it is very clear that it consists of all the partial derivative of all the components of f, and arrange the partial derivative in this way. The row are the components of f. The first row of this matrix is the partial derivative of the first components of our vector valued function f, right? And the last row is the last the partial derivative of the last component fm. And the column is counted by independent variable. Okay, the column is counted by independent variable. The first column is the partial derivative of each component of f with respect to x1, until the last column is the partial derivative of all the components of f with respect to xn. So this is n and this is all n, right? So this matrix is very clear. It is called the Jacobian matrix of our vector valued function. This is a very useful concept in multivariable calculus. So in a special case, if m equal to n, this matrix is a square matrix, right? For square matrix, we have a determinant. So we can talk about the determinant of this square matrix. If m equal to n, we use this notation. Of course, determinant of this matrix, we denote this by JFA, right? The determinant of this square matrix denoted by JFA. This is the what is called Jacobian matrix, Jacobian determinant, or simply Jacobian of f at this point a. Okay, Jacobian, a very important concept. We have Jacobian matrix. If m equal to n, then the Jacobi matrix is a square matrix. Its determinant, denoted by JFA, is called the Jacobian of f. Okay, and for the Jacobian of f, our this notation, either this one or this one are very brief, very compact. But sometimes we need to denote, indicate the component of this. Therefore, we also introduce a notation. This can also, sometimes it also be denoted by f1 fm over x1 n, not m. Our m equal to n. Okay, and to indicate this is taken at the point A, so we write an A here. So this notation are also frequently encountered, also used very often. Both of these are the Jacobian of F, which is the determinant of the square Jacobian matrix. Okay. So these are very elementary notation in multivariable calculus. So in our study of linear algebra, we see that the Jacobian matrix can be considered as a linear map from Rn to Rm. It maps a vector V in Rn to the multiplication of the Jacobian matrix and the vector V. This multiplication is a metric multiplication. It is reasonable because here the Jacobian matrix is n by n, and the vector V is n by 1. So the result is an n by 1 vector, which is an element of Rm. And this mapping is linear, as you see in linear algebra. So this is a linear map. Linear map are easier to study. So it turns out that this linear map provide a very good. This is a linear map. Okay, which is a very good approximation of our nonlinear map. Of nonlinear map. Nonlinear. Nonlinear map. Which nonlinear map? This nonlinear map is the nonlinear map we talk about apply to a vector h in Rn being mapped to minus Fa. Okay, so this nonlinear map can be approximated very well by our by the linear map determined by the Jacobian matrix. Okay, so this is the fundamental idea of derivative of multivariable calculus. Okay, we will study the nonlinear map. This is essentially our original map F. We will get a local property of this nonlinear map by the study of the linear approximation, which is our determinant, which is the linear map determined by the Jacobian matrix. Okay. So roughly speaking, if the linear approximation, that is this linear map, has some property, the nonlinear map, the original nonlinear map, will locally have this property. For example, we will prove that if this nonlinear map f prime a, the Jacobian matrix determined linear isomorphism, or it is invertible. So for example, if this linear map is invertible, then locally f is also invertible. Okay, we will prove this result in our study of the inverse function theorem, which is the very useful. Okay, so we introduce this concept, which we will use later, and we also mention some idea that will play a central role in our later study. Now I will, having studied this concept, I will introduce you to some example. from this example, you will see that the differential calculus for multivariable function is a very rich, very interesting theory. Okay.